Now, when an object changes shape, we say that it's been deformed. But importantly, there are two different types of deformation that you need to know: elastic and inelastic. If an object returns back to its original shape after the forces have been removed, then we call it elastic deformation, because it's able to spring back like an elastic band. However, if the object doesn't quite return to its normal shape and stays deformed in some way, then we call it inelastic deformation, or sometimes plastic deformation, because it keeps its shape like plastic. The next concept we need to look at is extension, which is the increase in length of a spring when it's stretched. For example, if we hang a spring from a solid support, then we can measure how the spring's length changes as we add downwards force to the bottom of the spring. Now, even before we've had any chance to add force ourselves, the spring's own mass will be exerting a force downwards in the form of weight. And this means that the natural length will be a bit shorter than the spring itself, because there will already be some extension. This extra length is generally pretty small though, so we tend to ignore it and think of the entire length as the natural length. If we then add a mass to the bottom of the spring, the weight of that mass will pull on the spring and so increase its length, which we can then measure as the extension. One thing to point out here is that the solid support will also be exerting an equal but opposite force upwards. And this is why the spring doesn't fall down when we add any mass. It's being perfectly balanced by the support. As we increase the force on the spring, for example, we add more mass, the extension increases proportionally, which we can write as F is proportional to E, because F is the force and E is a symbol for extension, although you might sometimes see it represented as an X instead. Exactly how much the spring extends, though, for a given force, depends on the particular object's spring constant, which is denoted by the letter K. And if we add this into our force extension equation that we wrote in the bottom left, we get F equals KE, with K being measured in newtons per meter and extension in meters. The spring constant tells us how many newtons it would take to stretch the particular object, like this spring, by 1 meter. So the higher the spring constant, the stiffer the material, because it requires more force to stretch it. We can show this relationship by plotting a graph of force against extension. As the force increases, so does the extension. And because it's a straight line that passes through the origin, we can tell that force and extension are directly proportional. We call this relationship Hooke's law. And importantly, all of this deformation will be elastic deformation, meaning that once the force is removed, the object will return to its original shape. There is a limit to this relationship though. At some point, our line will start to curve, and we call this point the elastic limit, or the limit of proportionality. After this point, Hooke's law no longer applies, and the object won't necessarily go back to its original shape, meaning that it will have been inelastically deformed.
The relationship between spring extension and applied force, and therefore by measuring spring extension, we can measure applied force. In order to do this, we have to know the precise relationship between spring extension and applied force, and to establish this relationship, we need to conduct an experiment. So as part of our experiment, we need to measure spring extension. You can see on the spring balance we have a scale, which measures the extension of the spring in millimeters. we see that we have zero extension of the spring, as shown on the scale, when zero force is applied to the end of the spring balance. In order to establish the relationship between force and spring extension, we will plot these on a graph. The vertical axis will be the applied force F in newtons, and the horizontal axis the spring extension X in millimeters. The first point for us to plot on the graph is zero extension for zero applied force. If we now apply a force of 5 newtons to the spring balance by adding this mass, which is a weight of 5 newtons, we see that the spring extends by 50 millimeters. When the mass comes to rest, the applied force, which is a gravity force of 5 newtons vertically down, is being balanced by the restoring force of the spring, which is 5 newtons vertically up. So let's plot this point. That is 50 millimeters extension for an applied force of 5 newtons. Now let's add another 5 newtons to the spring. Can you guess how much it will extend? As you can see, it has extended another 50 millimeters, so that the total extension is 100 millimeters for a total force of 10 newtons applied to the spring. So let's also plot this point. Now you can see that the 3 points lie on a straight line. This is very important, as it is the principle on which the spring balance works. It simply says that the relationship between force and extension is linear, and that is why the spring extended by the same amount each time we added 5 newtons force. This linear relationship between force and extension is known as Hooke's Law, after Robert Hooke, who discovered it in 1660. As Hooke's Law is a straight line, we may express this mathematically as the applied force F equals a constant K times the spring extension X. The constant K is known as a spring constant and is the ratio between the change in spring force for a change in spring extension. Mathematically, it is the slope of the line in the graph, and it is a unique property of each spring. So you can calculate the spring constant by calculating the slope of the line. To do this for our spring balance, we divide 5 newtons force by 50 millimeters extension, which gives a spring constant K equal to 0.1 newtons per millimeter extension. This means that we can calculate the force on the spring balance using Hooke's Law in the form force F equals 0.1 times the spring extension X.